So away we go. I am deliberately tried to create an opportunity for lots of questions and answers. I think that will be the most valuable way to serve your needs and interests. So don't be shy when we get to the end. There should be plenty of time. Um, I wanted to start with this. The fact is, what the DOE had been doing last year was nowhere close to enough. We just needed way more investment. Even with a doubling of the DOE budgets, we are not on track to hit key climate goals. And part of the reason why is that, we just need a lot more stuff. The International Energy Agency's pointed out that we're not on track for almost all of our technologies, and half of the reductions we need to get are from technologies that have not yet come fully to market. They're not fully commercial. So we need to put more money into the system to make things work. And there's a second reason to do that, not just climate, but competition. Right now, many other nations are basically much more heavily invested than the United States on an innovation agenda in energy. China is the obvious one pointed out here, but frankly, if Hungary and Estonia are doing more on a per capita basis than we are, perhaps we could do a little more. As you well know, the United States is well positioned to lead. And so we recommended in Energizing America tripling the R&D budget. And in doing so, we'd get about 1 million jobs out of the system, as well as export technologies and a lot of other stuff. In that report, we pointed out that that's well in line with other stuff we've done in the past. Basically, if we tripled our current budget, it would still be half of what we spend on healthcare R&D. So way less than we spent on things like Star Wars or Manhattan Project or Apollo Project or other things. It would ballpark out at about 0.1% of GDP, which seems like a fairly low-level commitment. Thankfully, we're starting to see these things coming forward, both in conventional appropriations as well as the bipartisan infrastructure package. There will be additional incentives for innovation coming out of the Build Back Better plan, assuming it's legislated. In that will also be additional revenue enhancements and tax credits and other kinds of good stuff to help kickstart deployment and innovation. And in that context, I'm very pleased to see a certain amount of that going to very tough problems in industry. This one is one of my favorite topics, heavy heat from heavy industry, industrial heat. Basically, industrial heat emissions are 10% of global emissions, which means they're more than all the cars and all the planes combined. Most people don't know that, but the people on this call hopefully do. Most people don't go to the store and buy 10,000 tons of concrete or steel, so that most people don't know it. But it is, in fact, the case that there are these huge, huge needs to decarbonize just something as simple as the burning rocks that we used to melt rocks today. In that context, I wanted to talk about a bunch of different things. Where is the clean energy going to come from? And I tend to think about these in terms of the energy services, not so much the fuels themselves, but really how is the clean energy, provide the energy service? And that could be heat or that could be work. But in either case, what's the thing that you need? You basically need 4 things. You need zero carbon power, you need zero carbon hydrogen, you need some fossilist CCS, and you need some biomass. That is the full it, by the way. There aren't other things. That is the full list of ways that energy services can come into the economy. It is possible that at some point we might use nuclear heat, but at this point, nuclear is entirely about zero carbon power. Now, when you talk about what fraction of the economy these things will look like, you're mostly here talking about 40% zero carbon power as a service. That's basically today's grid plus EVs plus a bit more. About 30% hydrogen, about 20% fossil to CCS, and maybe something like 10% biomass. I think it's just easy to remember these 40, 30, 20, 10. It is also the case that that's about what the Net Zero America report from Princeton came up with. They have very similar numbers. This is not that different from what the International Energy Agency's scenarios have. To make zero carbon power, We will use all kinds of things. To make zero carbon hydrogen, we will use more zero carbon power. Like, we all know that. But this is the energy service mix of what's going to go into the world. That will involve some carbon capture and storage across many disciplines. It will involve using wastes. There's a bunch of stuff that's going in here, but I want you to keep these numbers in the back of your mind as you think about your own companies, your own industries, your own pilots. This is what you got. So, what does it take to do the job? And I wanted to, again, start with low carbon heat for heavy industry because it's just a nice place to start. Again, not a lot of options for low carbon heat. One of the things that most surprises most people is that the quality of nuclear heat is so low that it can't actually provide heat, period. Maybe the advanced reactors will. They can get up to some good stuff, but for steel, for glass, for cement, for a lot of chemical processes, you're really talking hydrogen, electricity, and biomass are pretty much it. And of course, there's challenges with these things too. In the case of electricity, for example, not only is it expensive, but how do you get the heat into the system is a very, very tough problem. So even though these are the theoretical options, the actual options are smaller still and remain challenging for everybody getting into this business. So I'm going to go through a couple of these options quickly. Some of these have direct relevance to what you're talking about. Some of them don't. Ultimately, we need to combine a construction agenda with a reduction agenda, and carbon capture and storage is one of the ways to do that. I'm going to speak about this very briefly, just 3 or 4 slides, and spend most of my time talking about hydrogen. So part of the reason why is because carbon capture and storage is, in fact, a way to make low-cost, low-carbon hydrogen. That's a good thing to do. It is also a way to get things like CO2 removal in the forms of, say, direct air capture or bioenergy with CCS. And these plants are built. There are zero carbon steel plants in the world. There are low carbon fuel plants and chemical plants around the country and around the world. In many markets, in many circumstances, carbon capture and storage is in fact a way to make the energy transition cheaper and faster. It is by no means the only thing. It is by no means perfect for all cases or markets, but it's a good thing to have. Just a refresher, carbon capture and storage is carbon capture and carbon storage. The carbon capture is the concentration of CO2 from dilute sources, power plants or industrial sites or even the air. The storage is the deep injection into porous and permeable geological formations, always more than a kilometer depth, and you need good traps on top of it. In North America, we have, at a minimum, about 3 trillion tons of storage capacity, so we're not too worried about that. And in fact, the median value is estimated at 8.5 trillion tons of capacity. So I think that'll do the job for a while. I can talk about specifics of this later. The main thing I want you to know about carbon capture is you can do it all over the world. There's already 24 operating facilities now. There's 65 in advanced planning. There's just a lot going on. So this is well understood technology. The regulations are very much in place. You can buy a unit with a performance guarantee and a wrapper. And increasingly, there are policy incentives around the world, and especially in North America, to do such things. The only thing I really want you to understand from CCUS is it's mature and a cost-effective way of reducing. That said, it's not what everybody needs and what everybody wants to use. For a lot of low-carbon power and a lot of low-carbon heat, hydrogen delivers in a big way. These features are ones you are already familiar with to some extent. When you use it or when you burn it, you emit zero carbon at the source. It is not just zero carbon, you also emit zero VOCs, zero particulates, zero sulfur, like the criteria pollutants from hydrogen use and combustion at its point source are also zero. It is the Swiss Army knife of the net zero economy. In terms of heat, it burns plenty hot. When you burn it, it burns at 2100 Celsius. If you burn it in oxygen, it's 2800 degrees Celsius. That's hot enough for pretty much everything. You do need some special sensors and controls if you use it. It burns invisibly. It turns out those things exist. They've been in the market a long time. One of the things we've learned is that ethylene crackers have byproduct hydrogen, and for many years, the chemical industry has been recycling that byproduct hydrogen and using it to generate heat or other chemicals. So we know that you can do this and it works. So the whole question about low carbon hydrogen is actually about the low carbon inputs. Can you make enough low carbon hydrogen is really the question. And you need really low carbon inputs, electricity, fossil with capture, biomass, whatever it is. You need the low carbon inputs or else you do not have low carbon hydrogen. Part of the reason why this has achieved so much interest lately and has gotten so much attention is, in fact, essentially we're at TRL level 9. It is commercially available today in all of its forms. A quick review of how you make hydrogen. Today, pretty much all the hydrogen in the world is gray hydrogen. You input some fossil fuel, natural gas or coal, you input some water, out comes CO2 and hydrogen. I've simplified the chemistry there, happy to pull it apart if you'd like. Essentially, 98% of the hydrogen in the world today is made this way. Mostly from natural gas, some from coal and petcoke and other stuff. You can make low carbon hydrogen the same way as long as you capture and store that CO2. This is commonly called blue hydrogen. There are a lot of blue hydrogen facilities in the world today, more being built and announced. But basically, you can get very high CO2 capture rates doing this up to and exceeding 95% capture. Then the life cycle emissions are really a function of the fossil fuels themselves. What is the footprint associated with natural gas production? Is there methane leakage, etc.? Roaring from the back of the field is green hydrogen. Green hydrogen for many years was a curio. It was used for aerospace applications in high school chemistry labs. Now that the cost of low carbon electricity has dropped so much, you take some low carbon electricity and some water and boom, you got low carbon hydrogen. On a full life cycle basis, this looks pretty good. I'm happy to share other slides with you if that's helpful at some point. But again, it ends up being entirely about the footprint of the electricity. If you have low carbon electricity, then you have low carbon hydrogen. Last but not least is biohydrogen. You can take hydrogen, gasify it. Biomass, you can gasify it, do a water gas shift, and again, make CO2 and hydrogen. It is not a hydrocarbon, it is a carbohydrate. If you want low life cycle on this, you can get it by just using wastes, essentially agricultural wastes, municipal solid wastes, forestry wastes. And that basically, if you're using a waste feedstock, is born carbon neutral. You can basically combine that as well with carbon capture and then have strongly carbon negative hydrogen as well. As I said before, the technical readiness for all this stuff is pretty high. There are some interesting technologies like solid oxide electrolysis, which are not quite where you'd like them to be, but fundamentally, right now you can go out and buy PEM electrolyzers, alkali electrolyzers, you can buy autothermal reformers and steam methane units and carbon capture systems, you can buy gasifiers and water gas shift reactors. These are all commercially available today. I do want to point out, though, that there's a lot of stuff coming up the curve still. Everything from photoelectric splitting to methane pyrolysis to microbial catalysis. Like, there's just stuff out there. From an innovation perspective, that's good news because that will not only provide more options that can go into more applications, but also have the potential to further reduce cost and further reduce risk. As I've said several times now, not all hydrogen is low carbon hydrogen. If you're going to use hydrogen for the purposes of your corporate goals, for the purposes of regulatory fix, for the purposes of selling green products, you want to make sure that you're doing the work. So, how do you get low carbon hydrogen? Well, there's a couple of ways. First, you can just start with fossil fuels. Those emit a lot. I've represented these numbers here as emission intensity, kilogram CO2 per kilogram of hydrogen. A lot of people do this as grams per megajoule. It's all, one thing or another. But here, this is just carbon intensity, tons of CO2 per tons of hydrogen. And basically, for most fossil gas technologies, 8 to 10 tons of CO2 for every ton of hydrogen. For coal, it's more like 22. But you can get high capture rates and low upstream emissions and basically get very low, 1.5 or so, to low enough to really be low. If you use zero carbon electricity, that's electrolysis with 100% renewables, for example, you get zero carbon hydrogen. In terms of scope 1, there is some life cycle emissions that go with that, but they're small. Again, you can get less than 1 if you do the job right. However, if you're pulling off the grid, that is not the case. If you're pulling off the grid, the carbon intensity can be much higher. In fact, just conventional grid electrolysis is in fact worse than coal in most markets. And even renewables firmed with gas is worse than gas. So you have to be very careful about how you source your electricity if you want to claim emissions reductions. As I'd said before, biomass is kind of born neutral. In part, that is based on avoided emissions from methane, but mostly it's just that you're dealing with wastes. If you add carbon and capture to that, though, you can get very, very low carbon systems. So biomass gasification with a fluidized bed gasifier, for example, with CCS, removes more CO2 than a conventional system emits. I mention this not because I expect you're going to organize your business practice around this, but it does mean that actually a small amount of this as a blend stock goes a very long way. You can get sort of this stuff or hydrogen from any of these sources and mix in a little bit of that stuff and be really quite low. And as you're thinking about long-term strategies in terms of how do you get beyond zero or how do you really squeeze the carbon out of your entire supply chain, I believe that at the end of the day, green hydrogen is going to win all of these things. By 2050, green hydrogen will be the cheapest of all options. But in the meantime, there's a lot you can do with the blue and with the biohydrogen that will help. One of the advantages blue hydrogen has today is scale. These are the big blue hydrogen plants that are operating around the world. There's been a handful of new ones that have been announced as well. And these things are making, hundreds or even thousands of tons a day of hydrogen with a mix of different capture rates from very high to modest. But you can get a big scale plant up and running pretty much right away. Green hydrogen, we do not have that yet. The largest operating plant is Fukushima. That basically makes 2.5 tons a day. So about 100 times less. Even in something like the Air Products case, you're talking about 200 times or 400 times less. Like, it's quite a lot less. That said, a lot is getting built. Many of you, I'm sure, have heard of the NEOM project in Saudi Arabia. That is going to come online in 2025. ThyssenKrupp just put out a bid for $2 billion worth of green electrolysis on this. That is a $5 billion plant. When it's fully built, the $5 billion will deliver 650 tons a day of hydrogen. That is absolutely commercial scale. There's also larger projects out there, AREH, the Asian Renewable Energy Hub in Northwest Australia. That'll be ballpark 7 or 8 times bigger. So, and that is a $40 billion project that will deliver 26 gigawatts of hydrogen. So there's a lot that is being planned, and a lot of these plants are being announced really every day. There was recently a $15 billion plant announced in the United States. We're going to see more of that as we go forward. Today, all the challenges are cost. Challenge today is cost. If you didn't catch that, cost is the challenge. And until very, very recently, there was basically no way to collect a green premium or an incentive that would manage those costs. These are US kind of prices. Gray hydrogen is about $1.20. Blue hydrogen is $1.60 to $2. Green hydrogen is, 5 to 8 in most markets. So quite a lot more. Part of the reason why is because most of the cost is the electricity cost. I want to say this again. Most of the cost is the electricity cost. Depending on where you are and what you're doing, 50 to 70% of the cost is the electricity cost. Ballpark 20 or 30% of the cost is the electrolyzer costs, What that means is if the electrolyzer cost today went to zero, green would still be very expensive in most markets. So really, the electricity costs are the things that need to get stuff down. And there's 15, 20% for the balance of plant. It is also the case that we have not yet created the supply chains for these things. While I am very enthusiastic about the gigafactories and the big production lines that have been announced, today there are limits in terms of electrolyzer supplies, fuel cell supplies, other things. The last choke point we're going to come across is infrastructure. And that little acronym there says every week is infrastructure week. We are going to have to build a lot of stuff, transmission lines, CO2 storage systems and pipelines, electrolyzer stacks, etc. It's just going to be a pile of work. Whether I'm optimistic or pessimistic, the work looks the same. If you can manage the cost, if you can build up the manufacturing limits, if you can get the infrastructure built, then in fact hydrogen becomes wildly important and valuable. In order to make the electricity cost reasonable, you actually need the high capacity factors too. A lot of people talk to me about the idea that you can do this with curtailed power. I don't generally think that's true, and this is the reason why. If you have a high capacity factor, then you're making good use of your electrolyzer investment as a return on capital. You can make $2 per kilogram hydrogen if you have 3-cent electricity. In order to do the same thing with, say, a 20% capacity factor, or a mix of curtailed wind and solar, for example, you need half-cent electricity. Half-cent electricity is hard to find. I want you to keep these numbers in your mind, though. The prices for green hydrogen that I've talked today are average prices. They are not necessarily project prices. It is increasingly the case that people are finding little X's on the map where there is really cheap electricity, where they can get a deal on electrolyzers, where they can get a tax break and make a project work. I'm sure that some of the people on the call are working these things for real right now to nail those things down. I will talk in a little bit about policy options that are coming forward too. The hydrogen hubs in the bipartisan infrastructure package are one. Hydrogen production tax credit 45X, which is proposed under Build Back Better, is another. There's many ways to imagine the cost for this stuff coming down through policy support. The cost of the footprint vary a bit by technology, and these are for different grids. And then these are renewable emissions intensities. Just wanted to give you a sense. Coal gasification is green, SMR is orange, and the goldenrod color is SMR with CCS. And in fact, if you can get this committed zero carbon electricity or renewable supplies, you can get very, very low carbon intensities. That's the job. Today, the average prices, again, these are average prices in the US, are pretty high. Same thing in Europe. Average prices are pretty high. And this is the split between the electricity costs, capital costs, and fixed OpEx. It is also the case, we did some Monte Carlo analysis to try to figure out what the future costs might look like. This is with inline sort of learning curves for renewable power, inline curves for electrolyzer cost reduction. And based on the assumptions that we put in, you're still talking $4 in the US. Let me say though, $4 is a whole lot better than $9. So that's pretty good. It is also the case that by 2040, almost certainly, this will the electrolyzer and green hydrogen costs will be low enough that they will always be cheapest. Even in this circumstance that we did, there's quite a range. And you can see that there are going to be places in a very close term where we will see green hydrogen cheaper than other options. And of course, this is unsubsidized. This is not policy dependent. If you added, for example, $3 per kilogram to this, then green hydrogen jumps right to the front. It is suddenly a lot cheaper to do a lot of things. I will say that the infrastructure costs are things most people are not paying attention to. For a company like yours, that shouldn't surprise you because you're not paying for the infrastructure necessarily. But if we want to really get very large fractions of green and blue hydrogen deployment, the infrastructure costs are going to be in the trillions of dollars. And some of that will be transmission, like just electrolyzer transmission alone. Electricity transmission alone could be as much as $3 trillion. A lot of it's the renewable build and the electrolyzers. All of those things add costs. My expectation is that globally, we are going to see a mix of blue and green around the world. Mostly green still, probably something like 70% green. Reasonable people can disagree on that. But having a little bit of blue really saves infrastructure costs for real, and it saves system costs for real. And in some markets, it's the cheaper option. I wanted to talk just a little bit about a couple of heavy industrial applications. We are actually doing a project right now, and we have a report in review looking at decarbonizing the chemical industry. We're taking a look as well at things like glass and ceramics. But I really wanted to talk first and foremost just about cement and steel. Cement is a huge source of emissions, 6% of global emissions. Just the heat is 2% of global emissions. So the heat from cement is equal to shipping in planes. So the challenge here is there's not a lot of places you can put hydrogen. There's not a lot of options that you have for avoiding this in this system. And here, almost all of the emissions come from the emissions from the clinker production itself and out of the kiln. So even though you can do some stuff like put heat into the precalciner, that could be hydrogen, that could be biogas, there's other things. For the most part, you're talking about solid fuels in the actual rotary kiln. In a report that we published out there with the Japanese government, these are the kinds of numbers that you're seeing out there. If you want to get really, really low, you're talking carbon capture. If you don't have carbon capture, you do not get any of the process emissions from calcination. So in terms of what can you do with other stuff, with hydrogen, you can get some. You can reduce on the order of 30% with a mix of decarbonizing the electricity, using hydrogen of various flavors in there, either blending that into the using that in the precalciner in terms of using that in putting something like ammonia or a solid fuel into the kiln itself. There's ways to think about doing it. It is also the case that the footprints today ain't great. And so decarbonizing the process heat is just one of the things you can do. For iron and steel, most production around the world is still blast furnaces, basic oxygen furnace, BF-BOF configuration. We're getting some DRI production, direct reduction of iron. Those also require electric arc furnaces for primary iron and steel production. Obviously, there's a lot of electric arc furnace in the United States. There's a little bit of emissions that are associated from the electrodes and what they do, but mostly you're talking about the electricity footprint for the EAF. And these are the kinds of breakouts in terms of where the footprints of the different inputs land. This is the tough stuff. These are the things that are hard to do. Ultimately, there's just a lot coming out of blast furnaces. EAFs, not so much. And DRI plus EAF has real potential, but we have not yet really gotten there with what we need. So if you wanted to decarbonize steel, you don't have a lot of options again. So we looked at a couple here: electricity, biomass, hydrogen, and CCS. I'm sharing the hydrogen sensibilities with you now. In all of these charts, this is the tallest blue line, the sort of the middle blue is maximum potential, and then the next one is the practical reduction. The short purplish bar next to it is the cost of increase to hot metal production, and the goldenrod color is the cost of CO2 abatement. So if you put hydrogen, blue hydrogen, or green hydrogen into a blast furnace, you can get real abatement, 20%-ish, maybe. The cost of that will vary as a function of the cost of the hydrogen going in. If you're working with a DRI plant, different story. Here you're really talking about much higher levels of decarbonization potential. You're really talking about 60%, 50% decarbonization potential. That would, of course, have higher cost in terms of hot metal and costs of abatement. In all of these cases, you're really looking at the lowest end, $100 a ton abatement, at the highest end, almost $1,200 a ton of abatement. It ain't cheap. But again, not a lot of options, and this is where policy can help by reducing the costs of supply and reducing the cost of retrofit. Same thing for biomass. Biomass has a handful of options, not some, just mix of stuff. Here, the theoretical potential is pretty good, but the practical potential is way lower. When you actually start looking at the life cycle of biomass, it's a problem. And so you really need to work with wastes and only wastes if you're going to do anything here. You can get decent abatement potential here, but fundamentally, if you deal with land use change and the life cycle change, then you're in trouble and you're paying a lot for not very much. So from an abatement perspective, and in many ways from a cost perspective, hydrogen seems advantaged to biomass. When we look at all the options that are out there, fundamentally, to really get to zero over the long term, you gotta stack stuff. Hydrogen plus zero carbon electricity plus biomass plus CCS, you end up having to stack these things in order to get up to, high levels of abatement like 80 or 90 or 100%. It's just the only way to get there. In our reports, we've listed these both as costs of hot metal increase as well as costs of abatement dollars per ton, and we've just ranked these things in order. Ultimately, there's lots of things that you can do. We are still pretty bullish on hydrogen as the way to do this. And again, as the cost for green hydrogen drop, as the familiarity with these systems drop, we're going to see more and more adoption of this. It is where the puck is going, and so it's a good place to skate. I want to speak very briefly about carbon utilization, and I like starting with my second favorite thing, coffee. If you roast coffee, it emits 2 pounds of CO2 for every pound of beans you make. That said, you can capture that CO2, put it into a plastic, put it in a 3D printer, and make a mug to drink your coffee. None of that was really possible a couple of years ago, but it is possible now. There's a bunch of companies that have entered into this carbon to value space. One of the companies that I work with, Carbon Direct, has invested in a handful of these things. I wanted you to be aware that that's the case before I mention these. They make very different stuff. This company 12 makes carbon monoxide mostly, but they're looking to make methane and ethylene and methanol and other things. Lanzatech basically takes the carbon monoxide out of the top gas from steel mills. They use microbes to make ethanol and then turn that ethanol to jet or into chemicals. They recently inked a deal with Lululemon to make yoga pants out of steel waste gas. Carbon Cure takes CO2 and binds it into concrete. They have both ready mix and masonry stuff. They can put their materials into white paper production, etc. This is scaling up fast. They have 120 facilities around the United States that will accept CO2 and make low carbon concrete. If you don't want to make concrete, you want to make other stuff, carbon black, carbon nanotubes, other kinds of stuff. Solid Carbon is one of the companies that does this. They have a high bay plant in Utah. It's fully electrical. They're working these things up, and they can take methane or CO2 as a feedstock and make these kinds of products. Ultimately, you need to be clear about the fact that you're talking about small volumes with all of this stuff. With the possible exception of concrete, you're not going to, turn the corner on climate by making a whole bunch of yoga pants. Still, people are interested in getting value out of CO2 if they can, and increasingly we're seeing interest in e-fuels as one way to do this. If anyone here is an engineer, you know that the second law of thermodynamics is a harsh mistress. And because of that, taking a waste gas and turning it into a fuel is a thermodynamic loser. Nonetheless, it does seem like people are prepared to start paying for this. People including port authorities, airlines, shipping companies like Maersk. I couldn't have said that with a straight face 2 years ago, but I can say that now. So this is coming up the curve. And it's, again, renewable electricity gets cheaper. This will really become an option. To make e-fuels or to make most stuff, you need CO2 and you need hydrogen. Otherwise, you can't make the stuff you need to make. Our quick pass on this is that today, most of this stuff is not commercial. The only thing that's really commercial right now is actually carbon monoxide. It looks like you can enter the market with an electrocatalytic pathway to turn CO2 into CO. The other things, really, you look at concrete. Concrete is commercial too. And that's pretty much it. But there's a number of these things where you're not that far off. Methanol production, syngas, there's a couple, ethylene is getting in the ballpark. So if you're thinking about pilots, this is a good place to start thinking. Can I use hydrogen? Can I use CO2 to make a green product in a facility? Can I use these things? Can I harness the DOE programs in a way to make a better plant that actually does the job? This is another way to look at those same things. We put it, it's called estimated cost of production. That was the last slide, and we put that in a ratio at the market price, the ratio of ECOP to selling price. If you're below 1, you're in the money. And for our kicking around numbers, if you're within sort of, 3 to 7, then that's a good place to do pilots. That's a good place to think about how can you make other stuff. It is the case that almost all of these things are, again, dominated by electricity costs. So if you can get electricity costs, you can make it cheap. For these products that I talked about, the dominant cost is actually green hydrogen cost, which again is cost of electricity. So potato, that's where you're at. Oops. I'll go back here. In our report that we put out for Energizing America, we suggested that the administration should take on these technology pillars and reimagine the innovation program around the tasks at hand as opposed to the fuels. We put a lot of effort into industrial decarbonization as a topic. Carbon dioxide removal is another, carbon capture and use. Getting the systems of electricity, not just cheap electricity production, in place, clean fuels. We actually need to get all of these things. And as part of the principles that we laid out, we had sort of the technology pillars and 6 principles. A lot of these are put a lot more money in and share it. Towards that end, we recommended rebalancing the innovation portfolio to do more increase for these other things. And in fact, we strongly recommended an increase in decarbonization of heavy industry as a fraction of the system. As a percentage increase, we said, how about a 70% increase in fiscal 22? And I'm pleased to say it looks like we're starting to get those kinds of things in the system. It is also the case that we strongly recommended that there be bespoke money for pilots and demonstrations. We were glad to see those in the American Jobs Plan. We're glad to see that in Build Back Better. We're glad to see that in the bipartisan infrastructure package. So now the opportunity is right to do these things. Pilots can do all kinds of things. And I wanted to just take a little bit of time talking about some of these options. For the low TRL stuff, that's a no-brainer. Let's put some innovation into testing those things out. But there's a lot of work on hydrogen production and use that could be done just to integrate into existing systems. I said, like, you can put hydrogen into a blast furnace as if that was easy and we really understood how to do that. We don't. That is a good place to do a pilot. Same thing with fueling crackers. Same thing with putting it into boilers on college campuses. One of my favorites is actually F-gas destruction, at chip manufacturers. F-gas destruction is a large emissions requirement and a large source of emissions. Right now, that's being done with methane going into thermal oxidizers. You could put hydrogen into those. You could do a double win on that and make it both more efficient and better stuff. A lot of the innovation and pilots should go into balance of plant cost reduction. Can we recover any of the waste heat? Can we use low-cost materials to drop the capital costs of these things? As fond as I am of the hard technology, there's a lot to do in this other stuff. I don't want to write off the other low-carbon approaches either. Biocoke, for example, in steel mills is a good thing to look at for biomass substitution, and it gets some of the hard-to-scratch stuff. Working on more of these electrical pathways, for example, electric Haber-Bosch, this electrocatalytic ethylene production, molten oxide electrolysis. So for primary iron and steel production. There's novel CCS retrofit technologies out there for cement, for capture, for chemicals. There's all kinds of stuff to do out there. And there's stuff that we have not really tried yet. Chip manufacturing, pulp and paper, pharma. These facilities are also currently emitters. These companies want to do right. They want to lead the pack. There's opportunities to do pilots in all of these places, not just with hydrogen, but with the full set. If we're going to do pilots, we should do some stuff. One of the things we really need to understand is hydrogen leaking from production, from use? We don't actually have really good data on that. We monitor hydrogen today solely from the standpoint of safety, not from any other standpoint. We can certainly do better than that. Same thing with practices. We need to understand what works and what doesn't. We need to codify that. We need to share that with industry trade groups. We need to share that with young professionals who are getting trained in the field. We need to develop and understand these practices. Last but not least, we don't really understand the long-term performance, the risk of corrosion, all of these things as much as we would like. But that's true for existing technologies as well as the evolving technologies. It is a place to focus. I will say again, two of the companies I mentioned, 12 and LanzaTech, have agreed to partner with pharma companies to actually help them develop plastics and products that they can use.